So we're currently still waiting for the last people to get in. So the door is closed. So welcome to the ARIS Rollout and Wrap-Up event of 2021. I'm Otto Gachter. Most of you know me as the head of industry relations at ARIS. And yes, we're here today to give you an overview of our past year's successes, our past year's projects, but also what we plan to do in the future. We have a lot of hardware here. You see, not everything went according to plan entirely, and we have quite a story to tell. So our vision at ARIS is not only to build rockets, but to contribute to the advancement of life and take part in exploring its origins by developing systems meant for space. So we really want to go further, not only build rockets, but also make scientific contributions and build actual space hardware. More to that later. This year was the 4th year of ARIS, and we have grown a lot over the past 4 years. Currently, we are almost 300 members, and yeah, we have been to 4 rocketry competitions with our rockets. And we are currently expanding our network in industry and academia. Last year, we had 3 successful projects. This is the first time we have managed 3 projects. We had, of course, the rocket Pika, propelled by our developed hybrid rocket engine, Daedalus. And then we had Phoenix guided recovery. You see it on the top. Guided parachute system, which we hope to integrate in our systems soon. And last but not least, we not only had 1 rocket, but 2 rocket launches at EUROC this fall in Portugal. And for next year, we are continuing the projects we currently have with the sounding rocket project Helvetia, the hybrid rocket engine Astrea, and the guided recovery project Periphas. But also we are expanding to new projects more in research, more in space. So we also have launched this for projects for the liquid rocket engine development Lea, CubeSat mission SAGE, and Nautilus unmanned underwater vehicle for scientific applications in a few decades on icy moons in our solar system. And more to this also later. And of course, we don't also have new projects. We have a new board elected this Monday. So this is my last event as head of industry relations. Alex will take over for me. And you will get to know him later in this evening. So don't be surprised if you see a few new names in the future. And today's agenda, first we will walk you through our last year's projects and of course our big story at EUROC to tell you about our experiences, our emotional journey there. And then we will give you a short overview of our many new projects. These will be really short, and we hope to be on time, finished at 7. Now, I ask Pascal to come forth, and he will present you the Project Phoenix guided recovery project. Pascal, the stage is yours.
Thank you, Otto. Hello everyone. My name is Pascal, and I was the project manager of the last year's focus project about guided recovery. I'm happy today to present you our outcome of the project. I want to give you some impressions throughout the past year by highlighting some pictures. On the upper left corner, you can see our first integration test of a RAMIA parachute into our system, followed by a first deployment test at the facility of our parachute manufacturer. On the bottom left corner, you can see a set of simulations done for our guided recovery system. Throughout the year, a big simulation environment has been built to test the sensor pipeline and all the algorithms used to guide the system autonomously to the landing point. Then, on the right side, you can see the system built by Phoenix. And many parts have been manufactured by our sponsors. Besides, a small amount of parts have been manufactured by ourselves, as you can see on the upper right corner. And then in the middle, you can see our system prepared for a drop test at Schießplatz in Wichlen, in Glarus. Systems armed, 3, 2, 1, release. These were the last words we heard over radio by the pilots when the system got released from a helicopter of an altitude about 1,000 meters above ground. The tense mood in the team finally disappeared when seeing the beautiful main deployment of the parachute, followed by a guided flight and a soft landing in the snow. In our project, in our testing campaign, a total of 6 drop tests have been conducted. 2 of those were fully autonomous guided. Then we had 1 crash and several flights for open loop and several open loop flights for system identification. However, the aimed landing position was not reached at the end due to a lack of drop tests with fully autonomous guidance. Then, at this point, I want to thank all our sponsors for your ongoing support. Without you, this project wouldn't have been possible. And now I want to give you some impressions into our testing campaign. Enjoy.
That were some impressive pictures. So hello from my side. I'm Max Lieb. I'm the project manager of Euler Phase 3. And I'm going to tell you that the first part of our story at the European Rocketry Competition 2021, which happened just a few weeks ago in Portugal. So Euler is ARIS' third rocket. Rocket project started in 2019. It was designed to be ARIS' first supersonic rocket flying to 30,000 feet at the 2020 Spaceport America Cup. Unfortunately, that got canceled, but we did have a small-scale maiden launch in Switzerland in July 2020. But we still wanted to fly supersonic. So we went to Europe 2020. Unfortunately, we had a problem with our electronics and had to cancel the launch in the last minute. But yeah, we still didn't want to give up. So over the last year, a small core team reviewed, renewed, and extensively tested the electronics and the parachute recovery system with the goal of flying Euler once more. And that's where our story at Euroc begins, with October 1st, when we loaded all of our ARIS rockets and equipment onto a truck to be sent to Portugal. A week later, we as a team, including our pilot Globi, followed. And on the next day, Monday, the first day, all of ARIS, we just met for breakfast at our campsite. And then all of us drove off to the competition. So after an initial welcoming and safety briefing by the organizers, we spent the day presenting Euler to the other teams. On Tuesday morning, first was our jury presentation, and then Euler was the first rocket to be scrutinized in a two-hour-long flight readiness review, which we passed with only 2 minor action items. So basically, we were ready for launch. Wednesday, the launch day, we got up early to drive to the launch site and immediately started to assemble our rocket. After some imposed delay by the competition, we started the final integration and assembly of Euler. And although being pretty stressed, we were still all in great spirit. Then just on time, we started carrying Euler the 600 meters to the launch pad, where we mounted Euler to the launch rail and prepared the motor ignition system. And then finally, we lifted Euler upright. And we activated the electronics, listened that everything was beeping as it should be, and our job was done. Euler was ready to launch at that point. So I had to take a second to look back and admire what my team did for the last 2 years to make that happen. So we went back and waited 45 minutes until our launch window. At the visitors area you saw before, and at mission control where I was standing. And I was getting more and more nervous as the ignition system, which was supposed to ignite our motor just a few minutes later, failed to ignite a German team's rocket 3 times in a row. But then our launch window came. Our avionics team checked the telemetry one last time, and we gave our go for launch. The 10-second countdown started. Everyone was counting out loud. My legs were shaking.
3, 1, ignition.
And I thought, come on, ignite. So that was the second flight of Euler. The work of 2 years, and we thought we'd go out there and look for scraps. So a team of 6 people packed some large trash bags, some water, and boarded the recovery vehicle. But when we came to the touchdown site, we couldn't believe our eyes. Most of the rocket was actually lying there in one piece, with hardly any damage. You can see it over here. The motor section, on the other hand, had been damaged badly in a fire, which had started after landing. But as far as we can tell, had it not started the fire, it would have been reusable with by just exchanging 2 parts. Returning with the good news, the morale in the team was back up to where it was before the launch to figure out what had happened. So the next day, we spent carefully analyzing the recovered rocket, and together with competition experts, we were able to pin down the failure to one O-ring at the top of the motor casing, which failed and caused the whole sequence of events that happened later. So just to give you a bit longer overview over our flight, the motor ignited normally, and the flight seemed to start out fine, but a tiny stream of hot combustion gases got past the forward O-ring of the motor and started heating up the aluminum casing. At 0.7 seconds into the flight, the casing burst, or the casing failed, and the hot combustion gases pressurized the inside of the motor section, thereby separating the top part of the rocket. Then the top part of the rocket was just flying along while the bottom part, still accelerating, flew into the top part and flipped it around with a rate of more than 600 degrees per second, which effectively threw out all of our parachutes at once. At a speed of about 200 meters per second, both our main parachutes immediately ripped, but the drogue chute did its thing to slow down the rocket, while the motor section went on its merry way. The motor section then, at some point of time, the actual propellant flew out of the motor section, and both separately came down. So this wasn't quite the flight we'd hoped for, but personally, I couldn't really be sad. I'm amazed by what my team managed to do in those 2 years, and also after this flight, to have the drive to analyze it, to produce a comprehensive report that we're working on for the next teams to learn from what happened, and the support between my team members after this obviously not so happy flight. It's been great to work with them. And just in general, I joined ARIS 3 years ago for launching rockets. But really, I'm still here because of the great team. And that's where I want to hand over to Xeno.
Okay, so welcome from my side. I'm presenting today PCAR. We also went to Europe, as you can see here. You can also see here us with the trophy for the 9K hybrid rocket launch. And what was PCAR? Over the past 4 years, ARIS has built multiple rockets. But for the first time this year, we wanted to fly hybrid to 30,000 feet and recover all parts safely. And it all starts with this image. Half a year ago, a team of motivated 53 students, also part of this project was Daedalus, providing the engine, went all in for the mission to successfully launch this rocket. At this point, we unfortunately knew that the Spaceport America Cup wouldn't take place this year again. And also, after trying to make a maiden launch here in Switzerland happen, we tried all our best to use one final shot, which was Europe 2021. So 4 days before Europe, we went to Geneva, flew to Lisbon, and were already prepared for the best. We came to the site, we unpacked all our things, and displayed our rocket in front of all experts, all rocket enthusiasts, other competition teams. In total, 20 teams were there 3 of those were from Switzerland, showing that we can win multiple competitions, one in our competition, the 3-kilometer competition of EPFL, and of course Euler with the commercial off-the-shelf engine. Yeah, 24 hours before our first launch attempt, we had to go through a series of reviews, one of which was the flight readiness review, where the judges came and asked about our system. Since we underwent multiple reviews over the year, also with some of the people here today, we knew that our system would make it happen. Our rocket was the largest rocket at the competition, hence the draw to what we have built was immense. However, we had other issues. As you can see here on the top left, we had tried to get gas in Portugal, nitrous oxide, which provides the oxygen for our combustion. However, due to shortages in Portugal, we weren't able to get them, the bottles locally. Luckily, we had some really motivated drivers to get gas at a customs area where we had our gas locked up for a couple of days because we had to ship it very late at last minute. However, we were delayed. We knew it would be really hard at this moment to launch. We still made it happen. So we assembled the system fully and were ready to launch. Unfortunately, if you have followed the live stream, we weren't able to do so. This was mainly due to a minor failure in the ignition sequence where we didn't arm the rocket perfectly. However, at this low point, the team was still motivated to make this happen, even though we knew that this opportunity was lost. So a day, 1.5 days later, we sat together as a team at the campsite where we stayed, focused, going through all the procedures again, and attempting it for another time. So we went as the first team onto the site early in the morning, as early as possible. We had already everything there, our gas, our rocket, and assembled the system perfectly in time. However, we faced other issues. After going through flight readiness review again, we went to the launch pad and erected the rocket. However, we thought at this point, nothing can go wrong. However, a connector of the filling station, which connects our intermediate tank with the filling station, was broken. So under duress, within the desert, Adi here tried to cut a new thread into a connector which we didn't have a spare part with us. And we tried all our best to have our system ready, fully filled for launch. However, this didn't work. Luckily, through our system design, we were able to fill our rocket as much as possible, however, not to the fullest. Even more stress. 5 minutes before the launch, we figured out that the decoupler of the filling station didn't disconnect to the rocket perfectly. So under duress, again, Leona here pictured, explained to the judges how to disconnect it manually. And thanks to this person here helping us, we had this rocket on the pad, fully pressurized and ready to launch. So we all started a countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition. And Picard rose to the sky. And this moment was just immense, not only for us, but also for the history of ARIS. Since the beginning, we tried to build our own rockets, and with this year's team, we were able to successfully build a full system on our own, including the engine. all people, 53 people, went through so many steps to get there. And we had so many issues along the way. But we knew at this moment we made history. We couldn't believe our eyes as we read through the data and saw that we actually succeeded the trajectory we predicted. So we figured out that actually we made it to almost 6.5 kilometers, which was immense. And we knew that with this engine, we can even go higher next year if we would fill the system perfectly. As you can see here, we had the recovery of our payload, which you can see here later on. It survived the flight fully. However, some other parts, unfortunately, didn't make it. We are currently analyzing what the root cause is, but we think that with this year's team, we can already be confident that the next team will make it happen. But luckily, we knew, even though the system and the whole project had its bumps, that we still made it. We were super, super glad that it happened. And together with the other Swiss teams, we celebrated as both Swiss teams were able to launch hybrid rockets at a competition and be highly competitive compared to all other European teams. And then I'll end here. Again, the whole team together. Thanks to Euler, thanks to Heidi, thanks to Tel, and all other projects, IRIDE and Daedalus and Rea, we were able to be successful at this competition. And without you, all our sponsors, supporters of ARIS, this wouldn't have been possible. And thanks a lot. We are really excited for the upcoming years, and we hope to have you back on board again. Thank you.
All right, 1 second before. I tried to get through 5 minutes without coughing. It's not COVID, don't worry. Before we want to close this really, really exciting story of Euler and Picard at EUROC, we want to take a short look back at the flight we had. Analyzing such a launch, a bit simplified, gets you to 2 parameters. One, we have apogee, which Xen already mentioned, was impressively over 6 kilometers. And then secondly, total impulse. Total impulse you can imagine quite simply as for how long a certain force is applied. So take 5,000 newtons times 8 seconds, you get to 40,000 newton seconds. The second thing to note here is that these competitions limit you to a certain amount because rocket engines are classified into lettered classes, and we are only allowed to fly up to class O. Again, looking at this very, very nice picture that still gets me the goosebumps, I have one very nice piece of information to share with you today. Our flight at EUROC 2021 achieved a new world record. This is the highest a student-developed hybrid rocket engine has ever flown in this class O as just described. And I think this shows not only how much engineering goes into this, but how much blood, sweat, and tears went into this whole project over 1 full year. I now want to also look back at the engine development side. For those who don't know me yet, I'm Aaron. I was the project manager of this fantastic team. And if you would have told me last May when we were doing our static firings that we would still grow a lot closer with this team, I don't think I would have believed you. We were already very close friends back then, but now after going through EUROC preparations, being a week in Portugal, and just going through these intense phases, made us not only a great team, but great friends. Of course, not everything was great all the time. For example, during our static firing campaign, we had an issue, igniter blowout, where in the pre-combustion chamber, which would be right here, the pressure gets too high too quickly, and the igniter that leads to the fire in the combustion chamber is blown out. This looks something like this. And the second time. Even though these are very nice pictures and nice for us to look at now, at the time back then in April, this felt horrible. We thought, how do we fix this? This was 2 firings in a row where we just did not manage to get it right. As you know, we somehow managed to fix it with quick engineering and long hours, and only 2 weeks later, the system looked like this. That's impressive, right? At that point in time, we thought we were there. We just implement the damn thing and we fly. Of course, it's straightforward, right? This was obviously not the case, and there was tons of work, hours to be invested, integration tests to be had. And thanks only to the great support we had together with Team Picard, we managed to get to some point where the system looked like a rocket. This now is a cold flow test where we basically prepare for a firing, but then we just don't have nitrous oxide but carbon dioxide in the system to get procedures down, and also see if the ignition sequence works. Again, impressive picture, nice video, and we thought once again, all right, we're there. But you've heard the story. You heard how it went. It was a lot of work from this point to finally get here, where we can say we are now officially rocket scientists. And with that, I just want to take one last look at this picture, because this is what these projects come down to. It is great engineering, but you're also investing in people, and I once again want to highlight how grateful we are that you are helping us. We could not do it without you. Thank you very much.
Good evening, everyone. I'm Alex Brandes and the successor of Otto. Where do you put the... Oh, thanks. So yeah, with our old projects going to an end, we have now new projects coming up which carry on the work of last year and take over our vision of ARIS. To show you how our future will look like, we put together a roadmap of the vision of ARIS. Currently, we have 4 new new projects which are working on reaching the goals of the pillar in the transportation. There, the goal is to win in the year 2024 Spaceport America Cup. with one of our own rocket and an integrated guided recovery system. After this milestone, we tried to focus then on a new in-orbit technology, which is planned to launch in 2029. Simultaneously, ARIS decided this summer to initiate two new pillars, one in research and one in habitat. There the goal is to present in the year 2025 a full-scale demonstrator for Earth application, and then afterwards in 2029 a demonstrator for alien applications. We know that these two pillars are highly ambitious, but they will lay a foundation of space research within our association. We believe, or we want to become a leading knowledge center within Switzerland in aerospace, and therefore we believe that this broad range of knowledge in space research and technology is necessary. To give you now a better understanding of the near future, we will present to you our new projects, and therefore I will hand over to our Deputy PM of the team Helvetia.
Hi guys, I'm the Deputy PM of this current rocket team Helvetia. Who is Helvetia? Helvetia is an interdisciplinary team with 50 highly committed students from various fields, which is structured into different sub-teams. As you can see, we have management and SE, the project management and system engineer on the left. Then we have structures, which is responsible for building the airframe. We have a recovery team, which will bring back our rocket safely to ground. Then we have avionics, which is responsible for the software of our rocket. We also have a testing, safety and launch officer. Furthermore, we have a simulation and control team, which is responsible for detecting the different flight phases, and last but not least, the payload team. So what do we want to achieve? Helvetia aims for 5 particular goals. First, we want to gather data and for future rocket teams and write an impeccable documentation. Second, we want to recover all parts safely through through a parachute. Third, we will use a hybrid propellant engine. And fourth, as you can see, we'll fly a 4-kilogram payload to an altitude of 30,000 feet. And only if we reach all these points, we are able to not only participate, but to win the SA Cup 2022. The SA Cup is the biggest rocketry engineer competition where over 1,500 students will participate in New Mexico. So how do we want to achieve these goals? We are all aware that winning the SA Cup is not easy at all, but we are taking as much steps as possible towards by choosing reliability over innovation, by iterating on previous projects like Picard and learn from their experiences, by focusing on doing more testing to prevent failures during launch, by having a documentation task force to be able to come up with a great documentation and earn as much points as possible in the competition. And also by having ambitious goals. Because if we want to fly high and aim for the stars, rather ambitious goals than the easiest ones will help us to get there. So what are our challenges? First of all, we have COVID-19, unsuccessful launches, and a delay of a fully functioning system. How do we want to mitigate them? We will mitigate them by having regular reviews with internal and external experts and advisors. We have large buffers and a very flexible schedule. We will not only manufacture 1, but 2 rockets in case one fails, and we can use the heritage of ARIS for backup solutions. So why should you support Helvetia, and what's so awesome about Helvetia? As I said, we have several sub-teams working together on their own subsystem, which finally fits into a whole rocket. We have cool and very intense testing phases during various weather conditions, as you can see here, cold flow tests, but also hot firing tests. We'll have a maiden launch in Switzerland next year before going to the SA Cup in order to make sure that all subsystem works together perfectly. But we also want to see pictures like this. Pictures where you can see the previous rocket team, which is preparing before the launch at the European Rocketry Challenge. And of course, also incredible pictures like this from the launch. So you are not only investing in a rocket, but in people. People with a heart for rocket science and with the willingness to learn and develop during this very intense and awesome project. With your help, we can make this dream come true.
So, welcome everyone, also from my side. I am Caroline, responsible for the remote filling station and the sponsoring and finance of the focus project Astrea. Astrea is now the 4th generation of hybrid rocket engines at ARIS, and also a focus project. So, a focus project is a part of the final year of the bachelor's degree. We are 8 mechanical engineers. On the top left, it's me. Then we can see Chris, who is project manager and responsible for the grain. We have Dino, also here today, responsible for the fluid supply system. Then Elias, who is responsible for the combustion chamber and the ceilings. Giorgio is also here today, responsible for the nozzle and the testing. We have Mathieu, who is responsible for the data acquisition and control system. Max is also here. He is systems engineer. And Vishnu Sutan, who is responsible for the injector and the decoupling. So as this is a project that is built on previous years, we have our goals set pretty high. So as follows, we will be integrating our hybrid rocket engine into the rocket Helvetia, but not only that, we will provide enough thrust for them to carry a 4-kilogram payload to reach apogee of 30,000 feet. With that, we will win Spaceport America Cup 2022. And also, we will provide a thorough documentation and data acquisition for the previous years. In addition to that, we want to achieve a technical excellency award as we are deeply looking into all systems in the hybrid rocket engine. To give you a small glimpse of our engine or preliminary design, so we are planning on achieving a 6 kilonewton thrust for the given 4,960 newton seconds total impulse. Here you can see a preliminary design. So what you can see here, and what is going to be the innovation of this year, is that we are going to have a new ignition system, a completely new grain geometry and composition, and as well probably a new nozzle design. So with that, I want to encourage all of you to come to our preliminary design review on the 8th of November, as we would like to have feedback on our new system. And here you can sign up, and I'm looking forward seeing many of you there, and we are looking forward working with all of you in the next year. Thank you.
Thank you, Caroline. So, hi from my side as well. My name is Dominic. I'm the project manager of the guided recovery focus team, and this year we have named it PeriFAS. Now, to put a few faces to that badge, we're a team of 10 people, and we're 6 mechanical and 2 electrical engineering students from the ETH, and we have 2 systems engineering students from the ZHW supporting us as well. And our mission, simply put, is to guide and land a rocket safely. Now, that sounds very familiar. We're basically doing the same thing as Phoenix. We are the 2nd generation of this project. But the main idea is staying the same. We want to use a parachute, guide the rocket with motors that we will control with a control system that we are developing. So if everything's staying the same, well, what is there to do? As with any project, the biggest changes happen from the 1st to the 2nd generation. So we want to basically refine, redesign, and integrate a lot of changes. Phoenix has done a lot of work in the right direction, but we will try to make everything more efficient, more compact, and overall easier to work with. And hopefully we can have complete guided descent, which they have achieved twice, for every of our drop tests. And all of this includes completely redesigning our electronics, and taking an adaptive approach to our control system, which we can iteratively test. So a lot of testing will be going on. Now, next to all the changes that we will do in the existing system, there's the biggest difference, which I'm very excited about, is that we want to launch our system, actually. So with that goal, comes a lot of challenges. There's a small task of actually building a rocket for our system to fly on. We are already working with a few people in ARIS which are willing to help us. So that is well underway, and very excited for that. And also, that way our team expands, but the core team can stay focused on the main objective, which is to build a guided recovery system. Also, the separation mechanism, which is something Phoenix didn't have to do. They obviously, as you could see in the videos, they dropped their system with their small drogue parachute already outside. We'll be having to develop an innovative separation mechanism, or we're trying to do that at least. That is a very mission-critical function, so we have to make sure to test it thoroughly. Also, we have to make our system fit for launch. Fit not just in the sense that it fits inside a rocket, but also fit in terms of withstanding all loads and accelerations of a rocket launch. And we will achieve all of that through going through a thorough testing campaign, which we will do the same way, hopefully, as Phoenix, by dropping it from a helicopter. We also have an upcoming event this Friday, which would be our preliminary design review, basically the same thing as Australia. Would love to have a few of you there if you find the time. It will be held here at ETH. Just approach me afterwards or shoot me an email. And yeah, also looking forward to working with all of you. So thank you very much. And I'll hand over to the CubeSat.
Oh, nice. Go. So you're not handing over to CubeSat? Oh, you are. Sorry, we changed the... No, we changed the... I thought... Oh, sorry.
All right. So thank you also from my side for joining us today and for the opportunity to present our old and new projects to us. For those of you who don't know me, my name is Theodora. I'm the lead engineer for the payload of the new project, CubeSat, called SAGE, which is stands for Swiss Artificial Gravity Experiment. And this is, as already said, a new project at ARIS, the first multi-year project, and is all about building a satellite. So first of all, let's meet the team. We are a team of 15 to 20 ETH students who are working together on the whole structure of the satellite, the control, the navigation, the avionics, and of course also the payload. So first, about the satellite technology and industry. Satellites in general take advantage of the latest advancements in energy harvesting devices, embedded systems, data science, manufacturing technology, and are in general there to collect data for researchers so they can focus on problems like climate change or agriculture. In the last 3 years, there was a huge trend towards high-frequency launches, especially for small and low-cost satellites, which leads together with the technology I mentioned before for it to become a multi-billion-dollar industry. And our goal is to develop and operate a CubeSat for approximately this size. It's going to be 3 CubeSat units. And it is going to simulate an artificial milligravity environment, which can be found on and around small extraterrestrial bodies. And our top level goal is to elaborate the technologies I mentioned before and build a solid foundation for future projects, not only at ETH, not only at ARIS, but in general. And second of all, we want to pioneer the competence and the abilities to realize these kind of ideas in space and realize these experiments on such a small scale. Yes, as already said, our mission objective, we want to develop this kind of CubeSat, which has to withstand extremely harsh environments such as vacuum, temperature changes, radiation, and all of this while orbiting the Earth with a velocity up to 8 kilometers per second. We want to establish communication with the satellite. We want to be able to control it, so control the rotation, the pressure inside, the temperature, and so on. In the heart of the CubeSat, there's going to be a payload experiment with the secondary value to generate a scientific value. So we are now looking into the direction of cancer research, the senescence of tumor cells, but are also focusing on areas like fluid dynamics and geology. Yes, for the first year, we want to have a primarily design review data pack and have a full engineering model by the end of next semester. If you have any questions, you can contact me or the project manager, Dario. And yes, thank you for your attention.
So, okay, it's good. Yeah, so I was so eager to present my project, I couldn't wait my turn. So yeah, I will be presenting Project LEA today. LEA is also a new project at ARIS. LEA is not only my name, but it stands for Liquid Engine ARIS. On this slide, you can see the first liquid rocket engine ever built by Robert Goddard in 1926. This photo was taken by his wife just before they were about to test and fly the first or not fly, but to test the first liquid rocket engine. And on the second picture, you can see what the test stand for the first ARIS liquid rocket engine will look like, which will be built by Project LEA and hopefully ignite in 2022. So these are our project goals. First of all, we want to build a liquid rocket engine. As you've heard, ARIS has had so many successful hybrid rocket engines. We want to give students the opportunity to explore the field of liquid propellant engines and also look into cryogenic components. For our liquid rocket engine, we are planning to use ethanol and LOX as a cryogenic component. So yeah, once we've built this awesome liquid rocket engine, we also want to test it. And as some of our supporters might know, it's been rather cumbersome to test any rocket engines at ARIS before, so we want to make this easier. For this, we are building a mobile testing bench on which we can test liquid rocket engines, but also hybrid rocket engines. This test bench will be mobile, so we can move it out from the ARIS hangar at Innovationspark Zurich and move it straight out onto the airfield and fire our engines there. This will build a foundation of data and knowledge for future projects and accelerate the development of engines. This will always also give a lot of research opportunities. For example, people will have the opportunity to write their thesis in the field of propulsion and also do semester projects. Further, we want to develop a flexible data acquisition and control system, which will make estimating our state of the engine a lot easier, and also evaluating data of the tests during and after a lot easier than was before. So yeah, I keep talking about we and us. Who are we? This is a photo of some of the people from our team. We are a still growing team. At the moment, we are over 20 ETH and students doing their masters and bachelor in different fields. We have a lot of mechanical engineers, electrical engineers, but also computer scientists. We come from different backgrounds, but we share a passion for space, and we are eager to gain some hands-on experience in the field of rocket projects. As our team and our project is rather new, we need a lot of support, a lot of people who can give us feedback. So I also invite you to our preliminary design review, which will take place next week on November 8th, just before Astrea's preliminary design review. If you wish to attend, you can approach me afterwards or scan here. And also, if you want more information about our projects, there's brochures lying around at the entrance. You can pick one up and, or write me an email. Thank you. Yeah, my name is Leah, and I'm the project manager of this project. Thank you.
Can you hold it? Thank you. Hi, everyone. My name is Théo Scheffer. I'm the project manager and system engineer of ARIS's very first unmanned underwater vehicle project. Now you could wonder, why building an underwater vehicle within a space project? And I'll answer the question in a second. But first, let me introduce you our team. We are 8 bachelor and master students from ETH Zurich, and we are all very motivated by this thrilling opportunity to innovate in the fields of oceans and space exploration. Moving on to the project itself, we will define the project in 3 stages, according to the different time horizons. We can twist a famous quote about space exploration by saying that the Earth is a small pool of humanity, but mankind cannot stay in a small pool forever. So the long-term goal for our UUV definitely is the exploration of icy moon's oceans. Indeed, celestial bodies such as Enceladus are thought to host oceans beneath an ice layer. Our goal will be the collaboration with space agencies such as NASA to send our UUV to space, reach such icy moons, and explore their oceans in order to look for traces of life, mapping the floor, and understanding better our universe. This time horizon for this goal is pretty vague and probably decades away from us. But we should remind us that the Mars rover exploring the surface of Mars today were imagined 30 years ago. Therefore, in 30 years, the UUV exploring the ice moon's oceans will be the ones you're investing in today. However, other very ambitious goals can be also reached here on Earth. Exploring the polar under ice oceans is an excellent intermediary step by allowing us to test our UUV in harsh conditions. We will use this opportunity to help the scientific research by mapping the seafloor or measuring the water parameters to understand better first-rate topics like climate change. This could be done within 2 to 3 years, depending on how many people are interested in the project and would be willing to participate during the coming semesters. But since we have to learn how to tie our shoes before running a marathon, our first goal will be exploring the Lake Zurich here in Switzerland to test our design and develop our skills in the field of UUVs, so that the next generation will have a solid base of knowledge in order to achieve our midterm and long-term goals. As mentioned earlier, since we have a total freedom in the design of our UUV, we decided that we wanted to innovate. Therefore, we chose to work in collaboration with EMPA and Imperial College London to develop a very innovative solution in order to improve the currently existing underwater glider design. Underwater gliders are a type of autonomous underwater vehicle that don't use any motor to propel themselves. The propeller that you can see at the tail of this glider here, in the top right corner, is actually a water flow sensor, and it isn't used for propulsion. Instead, the propulsion of gliders is ensured by the control of their buoyancy. By decreasing its buoyancy thanks to pumps, the glider sinks, and this vertical motion is translated into an horizontal motion thanks to its wings. This is very energy efficient. However, an issue with this design is that the angle of attack of the wings is constant, and therefore can't be optimal to produce lift and minimize drag at the same time. For this reason, we are developing a very innovative solution based on the emerging field of soft robotics that allows us to control the shape of the wings and thus push the efficiency of the system to a level that has never been reached before. Your investment in our research may not only change the face of oceans exploration, but also revolutionize the aerospace and aircraft industry, since this innovation may also find its application in fields such as airplane design. We are all very excited about this project, and I'm looking forward to showing you what we will achieve this year. I will now hand over to Alex to conclude this presentation. Thank you.
So we are already at the end of the evening. As you probably realized, the number of projects and goals increased a lot this year compared to the last year. With that, this is the reason why our association in the few months grows up to a number of 300 members, and this number is incredible. However, with growth, success is not guaranteed. But the reason why we have been successful and we will be successful in the future is because we work together as an entity. The reason why we are able to launch rockets and try to recover them successfully is because we have such a strong and broad network of supporters and sponsors. Hereby, I want to thank you again for your support. I want to thank you especially to the advisor, the coaches, the experts, and all to our sponsors for your great help. Not only thanks to your financial support, but also due to the expertise and the knowledge transfer, we were able to pursue and fulfill our dreams. The dream of flying rockets, the dream of a space hub in the mid of Switzerland, focusing on research and space technology, and the dream of reaching the sky and going beyond. With these words, I will close this evening. Thanks for coming. Afterwards, we will have some food and drink in front here in the room. And if you want to discuss with you further about our projects or about the broken parts of the rocket, do so. We will be happy to answer your questions. Otherwise, see you soon and have a great evening.